Hello and welcome to episode 2 of CS350 Online. As always, I'm your host, Leslie Eisted. On today's episode, we're going to start our discussion of threads, and we're also going to take some time to show you how to open OS 161, run some of the test programs, and hopefully we'll even get an opportunity to show you how to run GDB on OS 161. But for now, let's start off today with our segment, the operating system of the day. Now, what's interesting about operating systems is that while many of us perceive that they're a fairly new idea, they actually go back to the early 1950s and possibly even before. One of the earliest successful operating systems was released in 1956 and was called GMNAA-IO, which is such a mouthful. But nobody, of course, ever accused us of being good at naming things. Now, this operating system was a joint development between General Motors and the North American Aviation Association. In this operating system, unlike modern operating systems, which can run on a variety of different hardwares, this operating system could only run on the IBM 704 machine, which you see pictured below. Now, when I say this was a reasonably successful operating system, what I mean is that it was actually installed on 40 computers around the world. Now, that probably seems like a very small number by today's standards. There are probably 40 operating systems in my house. I haven't counted. But this is 1956. People didn't have home computers or cell phones or things like that. So that is a pretty successful deployment to have 40 out there. Now, what is interesting about this particular operating system? As an early operating system, it didn't offer much to the user. It was a resident monitor, which was controlling what happened before and after each of the jobs were run. And it was also a batch processor, which means you give it a list of jobs and it will run them in sequence, one right after the other. Now, as its name would suggest, the third thing that this operating system offered was I/O libraries, which is a really, really big deal, because you don't want each and every single developer of every user application to have to redevelop how to write to a disk. Bad things would happen. So having that I/O library abstracting how storing files worked was a really useful thing. Now, you might be wondering what kinds of applications would they have run on this particular operating system. Well, in these days, you might have been looking at simulations. You might have been looking at inventories, computing payrolls, doing accounting, and so on. All right. So that concludes our episode of our operating system of the day. And now, let's discuss our previous episode. So in our last episode, we introduced how this course was going to run. And we also discussed information about our expectations of you, quizzes, assignments, and our final assessment. And we also introduced what an operating system was. Just to recall what an operating system was, an OS is a collection of programs and utilities with a kernel that creates an execution environment and loads programs, manages hardware resources and events, and provides an abstraction of those resources for user applications and interactions. All right, on to new content then. So we're going to talk today about threads and concurrency. But before I get into our actual slides on threads, which is module 2 on the course website, by the way, I'd like to talk a little bit about the origins of the concept of concurrency. So if you go back to the 1950s, when computers were the size of the packed gym and cost millions of dollars and hundreds of people to operate them, you can imagine that they didn't have a lot of processing power by today's standards. Now, many of these machines had only one CPU. And when a program was running, if they needed to do some kind of I/O operation, like loading some data or saving some data or sending data to a printing device. It took a really long time. Now, we these days don't think of sending a signal from our mouse to our computer as taking a long time. We don't think of things like saving a text file to disk as taking a long time because the disk is inside of our laptop or our desktop. It's right there, and all of the different buses that connect the pieces together operate very quickly. But in the 1950s, this wasn't the case. Your disk was a refrigerator-sized unit on the opposite side of the room. And in order for that save signal to go from the CPU on one side of the room to the other side of the room, that signal actually had to travel along the wire. And sending a signal along a wire is not free. It takes time. Not to mention, you probably can't continue executing your program until the save is completed. So the CPU would sit there idle while the disk saved whatever it was you asked it to save. And people started to realize, if I'm just having my CPU sit idle while the disk takes half an hour to load something, couldn't I make better utilization of that CPU by running another program? And so this is actually called multi-programming. It means that we're going to improve the utilization of our CPU by whenever it is idle due to an I/O operation or some such event, we're going to choose another program to run in the meantime. Now, does this improve performance? Not exactly, but it can improve the utilization of the CPU. And when you're looking at an era of CPU time being so costly, this was a really big deal. And this concept of multi-programming is actually where the idea of concurrency originated from. So then, let's actually start talking about threads and concurrency. All right. So the first thing we should ask is, what is a thread anyways? Well, the truth is you've been using threads your whole life, of programming that is. Assuming you've been programming your whole life. Maybe you haven't. A thread is just a sequence of instructions. Just a sequence of instructions. And every program that executes has to have at least one sequence of instructions, which means every program has to have at least one thread. Now, we can give a program multiple threads, that is multiple sequences of instructions. And when we do this, we can actually achieve a lot of really, really interesting things. For example, we can have multiple threads to improve our CPU utilization. Think of it this way. We can take each program as being a single thread and just do multi-programming, which gives us better CPU utilization. Which indeed, by the way, is something that your CPU is going to use. But we can do some other things with multiple threads. For example, as I've already mentioned, CPU utilization can be improved by using multiple threads, be they in a singular program or across multiple programs. And it's not just CPUs that we can improve the utilization of, it's all other kinds of resources in our system as well. We can improve responsiveness. That is, we want our user interfaces to respond very quickly when we tap on a button or click on a mouse. And so we can use multiple threads to improve that. Threads help us express concepts like priorities. They're also really good for modularization. For example, if you have a video game, you're going to have some back-end logic related to the artificial intelligence of your enemies. And you may also have some logic dedicated to rendering. Now, those two things are very, very different from each other. And so we might have separate threads to modularize the tasks or responsibilities that are going on in that game. Now, of course, one of the big reasons why we have threads is for parallelism. That is the ability to actually have multiple threads running at the same time, not taking turns, running at the same time. So let's actually see what that means. So I'm going to switch over here to my terminal. And I'm going to open up a lovely little program that I've written, and it's written in C++. It doesn't do much. So this program is called No Threads, because it has no threads. And we have this image here that's 40,960 by 2,160 64-bit integers in size. And we are going to create a big block of these using malloc, and then we're going to fill it in with values between 0 and 255, and then we're going to call this function called swap colors. And for each 5 that is in the image and 10, we're going to swap them. So 10s become 5s and 5s become 10. So here we have that, and then we're just going to do a bunch of silly, extra busy work. Okay, this program doesn't do anything. So this program has no threads, well, no extra threads. It's going to be one thread. Let's run this program and see how long does it take. Now you'll notice here in the bottom of my window, I have top open. This program is called No Threads, and I'd like you to watch and see how No Threads rises up. And it's going to end up, you'll be able to see how many threads it's using and how much memory it actually has. So let's run No Threads. It might fight a little bit with OBS here at wanting CPU time. So you can see here that is using 99.7% of my CPU time. And it has one thread, and only one thread is running. Now you might be noticing something else interesting, that the sum of percentages of CPU time that's being used between OBS and No Threads is more than 100%. And that's simply because this is a 6-core machine, and each of those cores has 2 parallel threads. All right, so our No Threads finished executing, and you'll see it took 22 seconds and change to run. Now let's look at our second version of the program. Now I've chosen to use a multi-threading tool known as OpenMP because it's cheap and it's easy to use. And so I have taken the same code from No Threads and I have added one tiny line. You'll notice this preprocessor directive here, pragma OMP parallel 4. That is going to tell the system to take this for loop and divide it into a bunch of threads. We also, of course, have to compile it slightly different to tell the compiler that we need to use the OpenMP library. Now, again, I'm going to run this, and I want you to watch top on the bottom so that you can see how many threads actually run and what percentage of CPU time it ends up using. There we go. There you go. Threads is using 12 threads. And it's done already. Completely done. It took 4 seconds. So, one teeny change to my program to take it from a singular thread to multiple threads has reduced the amount of time it took to run the program by a factor of 5. It was 5 times faster to use threads than no threads. That's pretty amazing. So threads give us a whole bunch of wonderful things. They give us modularization, they give us better resource utilization, they help us with things like UIs, they also give us occasionally better performance. I'm going to kill top here now because it actually uses a fair amount of resources. All right. Now, a question you might be asking is, are there any interesting consequences of using threads? How do threads actually execute? Well, what I'd like to do is I'd like to open up OS 161 and I'd like to show you some of the thread demos. So let's go back to our terminal. There we go. Let's make it a little bit bigger here so we can see it nicely. And I'm going to go into the code directory. So I'll make this a little bit bigger just so you can see the text better. All right. Now you'll find the source code in the OS 161-1.99 directory. Now, OS 161 as a package gives you both user code and kernel code. You don't need to write any user code for this course, although being very familiar with what code is in there is very useful for some of the later assignments, as many of our tests are actually user programs. But for now, let's go into the kern directory. There we go. Now, we're going to run a program called thread test. You will find a number of kernel test programs in the test directory under kern. So let's go in there. Here's a bunch of different tests. The test programs that I would like to run for you now are in threadtest.c. Here we go. That's nice and clean. I apologize if you hear a bunch of excited laughs and giggles and screams. My kids are in the basement running wild. All right. So what I would like to search for in here is first, how do we create a new thread? It's very obvious that if we create any program, we will have a single thread because we need a program to have a sequence of instructions. So if we just write some regular code, that gives us one thread. But how would I create another thread on purpose? You saw me do it with OpenMP, which is a really lazy way of doing it. Really quick too. But how does OS 161 create a new thread? It uses a function called thread fork. Now, if you come down to line 105 in a function called run threads, you can see how OS 161 creates a new sequence of instructions that is a new thread on purpose. It uses this magical function called thread fork. Thread fork takes several arguments, and we'll discuss what those arguments are in a couple minutes. But first, let's actually look at the sequence of instructions that we are asking this thread to run. Now, in this case, I want to go to a function called loud thread. There we go. It's on line 57. Loud thread doesn't do much. It takes two arguments, a void that is called junk, and we don't actually need that. And because in OS 161, all of our make files have set warnings to be errors, any unused variable would actually cause a warning and therefore an error during compilation. So you'll note that all unused variables are cast as void to eliminate that particular warning. And please make sure you don't modify the make files to change that, and just cast everything as void as we have done already. We're not going to use junk. We are going to use the unsigned long num though, and what that's going to contain is the thread's number. When we create the thread, we can actually pass a value into that num there. So what loud thread does is it's going to turn that number from a number into an actual, or from a character into an integer, and then we are going to print it onto the screen 120 times. Don't worry about this V business down here. We'll talk about that another day. Now, what would you anticipate that the output is? If I create 8 threads and each of those 8 threads is going to print its number 120 times, what would you anticipate the output would be? Now, if some of you are sitting there and thinking, well, that's obvious, because if you create the threads 0, 1, 2, 3, 4, 5, 6, 7, then we should have 120 zeros, 120 ones, and so on and so forth. And that is a possible output, but it is very highly unlikely. So let's actually run this test and see what happens. So, in order to run OS 161, you're going to need to go into the root directory. Make sure that you've got all of your paths set up. And then you need to run OS 161 through the MIPS simulator. So you would type sys161, and then you need to specify which kernel that you have compiled that you would like to run. In this case, I'm going to run assignment 0's kernel because it has nothing implemented. I push enter and the operating system boots up. Now, if we had actually completed assignment 0, which I hope that you have taken an opportunity to do so, you would see instead of put your group name here, you would see your name. We're not going to be too fussy on making sure that your name is spelled correctly or that it is actually your name. We're just going to make sure that you have changed this. All right. So you'll see, of course, with version number, which version of the kernel you are running. Then you'll see a bunch of information about the different hardware resources booting up. And finally, you will see the menu prompt. Now, if you hit question mark, it will show you all of the different kinds of menus you have available to you in the kernel. For example, there's an operations menu. We don't use it. There is a kernel heap stat. We don't use that one either. The only menu that we tend to use here is the tests menu. So if you hit question mark T, it will show you all of the kernel tests that we have. And by the way, these are some of the tests, or at least a subset of these are tests that we will be running in order to test your kernel. Now, the test that I would like to run that corresponds to the code that we've just shown you is thread test 1. So at the prompt, what I'm going to type is thread test 1 as TT1. There we go. And there. What you'll notice is we don't get 120 zeros followed by 120 ones. We get the threads taking turns. 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. Now you might be thinking to yourself, okay, so they each get to print a character on the screen and then the next thread gets to go. Except if you look at the very end of the sequence, you'll notice it goes 7, 0, 1, 5, 6, 3, 1. Here's the truth. In a single CPU system, we can only run one instruction at a time, which means if I want to give the illusion that multiple threads are running at the same time, I have to alternate between them. That is, I have to give each thread a short period of time to operate, and then I have to give another thread an opportunity to run. And this has to happen at some kind of rate that's not really perceptible to your user. Now, that doesn't explain why things get out of order. It also doesn't explain why when I run this test again, we get a completely different ordering. Well, the truth is, how we alternate between threads, there's a variety of different ways that can cause us to change from one thread to another. Printing to the screen is one of the things that would cause us to change from one thread to another thread running. Because it's an I/O operation. Because it doesn't involve the CPU, which means the CPU would be sitting idle, and so we'll let another thread run. But sometimes it takes different amounts of time for that character to print onto the screen. And so we can get a lot of interesting variations happening here. You also don't know what other operations are going on in the operating system, which may cause certain threads to run a little bit slower or a little bit faster than we would anticipate. What I'd like to point out to you here is it doesn't matter how many times I run this program. You will note that each and every single time that I run the program, we get a completely different output. It's not that getting two outputs that are the same is impossible, it's just highly improbable. Now, on that note, if you're sitting at home and you've decided to start with assignment 1, which by all means, please go ahead and do so, I would like to point out that in this course you're going to find it is insufficient to run your program once or twice and then conclude that it works. You're going to have to not be, there's no way to prove it works other than to be statistically confident your code works. So it's very important in this course, due to the multi-threaded nature of it, that you run your program hundreds of times. And we'll talk more about that another day. All right. Now, we've run our thread test 1 here. How do you actually leave the operating system? To leave the operating system, what you want to do is type the letter Q. And the OS will shut down. If you see a message, the system has halted, you know that the OS is shutting down, and there's nothing wrong. All right. Now let's take a look at our threads a little bit more closely in OS 161. To create a new thread in OS 161, you're going to use the function known as thread fork. Now, this function here is not a function that exists outside of OS 161. There are many different threading libraries out there, and they each have their own way of creating a new thread. In OS 161, the function is called thread fork. Now, there are a number of parameters to thread fork, and we can look at them here. So thread fork takes 5 arguments. The first argument is the name of the thread. Now, it's very confusing because we might be thinking that the name of the thread is a unique identifier, but it is not. A thread's name is really just for the user and to help them debug. So there's never a guarantee that thread names are unique. So don't rely on them to identify a thread. Then we have the process. That is the program that the thread actually belongs to. The third argument is a function pointer. This is the starting point for the new thread's sequence of instructions. So we're going to pass a function pointer here, and the address of that function is going to be the starting point for that thread's sequence of instructions. So you'll note that when we call for thread test 1, loud thread was the function whose address we were passing through here. The last 2 arguments of thread fork are the arguments that we would pass through to the function pointer. So you can pass any kind of data and any kind of shape through the void pointer, and then a number if you choose. All right. Now, something else I'd like to point out to you about the thread fork interface here is that it is very important when you call thread fork that you match this signature exactly. And it's very important that these also match exactly, or you'll have a very bad time trying to compile things. Now, is that the only API function we have for threads available to us? Of course not, because there's other things that we need to be able to do with threads as well. For example, we need the ability to terminate a thread when we want it to be terminated. Now, if we didn't actually call thread exit, which will terminate the calling thread, would the thread actually terminate? Well, if it reaches the end of a sequence of instructions, that is, you pass it a function loud thread, when it reaches the end of that function, the thread would terminate. But perhaps we would like to force the termination of the thread early. Then you can call thread exit and it will terminate the calling thread. This is not a function I use terribly often. Another valuable function, which you probably won't use terribly often, is called thread yield. Now remember how I said that in order to give us the illusion that all of these threads are running at the same time, we're going to have the threads alternate. Thread 1, thread 2, thread 1, thread 2. What if thread 1 is running and it realizes, you know what, I'd like to voluntarily give up the CPU and let somebody else have an opportunity to use it? That's where the function thread yield comes in handy. So, thread yield we can use to give up the CPU voluntarily. All right, where would you use this? This is not a function that you use when you want to ensure that the running thread is no longer going to execute. This is when you want to encourage the CPU and the operating system to run a different thread. Where I tend to use thread yield is in implementing things like no hold and wait, which is a technique we'll discuss at a later date for deadlock prevention. We can also use it to mimic the behavior of condition variables. And again, we'll discuss what those are at a later date. Now, if you're interested to read more about how these functions operate, at the bottom of the slide, you will see where in the kernel you can actually find their headers. And in fact, all of the kernel's headers can be found in kern include. Now, if you are an individual who has done multi-threaded programming before, you're probably wondering, where's the join function? OS 161 does not have a join function. For those of you who are not familiar with this particular ability, the join thread function would force a thread to block, that is, wait until the specified thread has completed. For example, you might use this if you have asked one thread to save or to write some information to a file, And then the thread that forked, you want it to wait for the other threads to be completed its write before we actually finish and save the file and close it. So if you need one thread to wait for another, the join operation is typically used. We don't have this function in OS 161, but that doesn't mean we don't have the ability to simulate this behavior. We absolutely do, and we'll discuss how we use semaphores to mimic this behavior when we talk about synchronization. Now, you're probably sitting there wondering, how do I get some experience running threads on my own? I highly recommend that you take this opportunity to try to run a simple program in both OS 161 and on your host machine. The program that I would like you to try to write is known as a thread fork bomb. What you want to do is fork threads at a rate faster than they are terminating. How I like to do it is have a function that is recursive in the sense that thread fork runs the function that's called thread fork. See if you can write to this function. It's only a few lines of code for OS 161. And then on Piazza, let me know how many threads you get before OS 161 actually crashes. And then for some real fun, why don't you try experimenting with threads on your host machine? There's a variety of different threading libraries that you can use. A very common one is called POSIX threads or P threads. This is a very well-supported cross-platform library and offers way more features than we would ever ask you to use in this course, but it's a really good experience for you to use. So try to write your fork bomb for OS 161 and then see if you can run it in P threads. And then let us know on Piazza, were you able to run more threads through OS 161 before you had a problem, or were you able to run more threads through your host machine and P threads? Make sure you know how to terminate a program on your computer. Another way that you can create threads is using the tool that I used in our little demonstration earlier today, and that was called OpenMP. Now, OpenMP, like pthreads, is a cross-platform, very simple tool for using multiprocessing and threading. However, unlike pthreads, OpenMP operates largely as a bunch of preprocessor directives. You don't get the sophisticated level of control that you get from pthreads, but if you're looking for a quick and dirty way to create a new thread or to turn a for loop into a bunch of threads, OpenMP is going to be your best friend, and it's what I use most of the time. Another way that you can experiment with threading is by doing GPU programming. That is general purpose GPU programming, running regular programs on your graphics card. Now, why would you run a program on your graphics card that isn't a video game or for rendering? Well, here's the dirty secret. Your graphics card has way more cores than your CPU. Your CPU, if you have an i9 from Intel, has 6 cores. The computer behind me is one of these fancy AMD Threadrippers. I think it's got 16 or 32 cores. I don't remember. It's got a lot of cores. But do you know how many cores the GPU in that computer behind me has? It has over 1,000. That's how many threads it could run in parallel. So we have wonderful libraries such as NVIDIA's CUDA library that let us take programs that we would typically run on our CPU and run them in our GPU. Now, if you're wondering why don't we use then our GPUs as a CPU if they're so much more powerful, there are some tricky little details. For one, a GPU does not have branch prediction. Number two, threads on a GPU have to run in lockstep. That is, they kind of only have a single instruction pointer, which means that all threads on a GPU have to be executing the same instruction. Not on the same values, but the same instruction. That means that branching is particularly problematic on a GPU. And if you think back to CS136 at the beginning of the course before we let you use if statements, it was a very weird way of programming, and you probably thought to yourself, nobody ever does this? You're wrong. When we are writing code for GPUs, we often write codes without branches because it's going to decrease the performance on a GPU significantly. Now, How old are threads? The original concept of multiprogramming actually dates back to the 1950s. But the concept of a more modern threading environment, that is also very old. Modern time sharing is from the 1960s. So we're looking at technology that's at least 80 years old, or close to 80 years old. It's pretty cool. All right. What I'd like to take an opportunity to do now is to discuss how programs run. We're going to roll back our concept of threads and just do a little bit of review on threads themselves. Now, I can see here that the video feed is probably blocking part of this diagram, so apologize for the lack of continuity here in the video. Let's just move this over just a teeny bit. There we go. All right. So, how do sequential programs execute? Well, let's think of this at a very high level. You have, if you recall, the fetch execute cycle. The PC is going to fetch, the CPU fetches an instruction, whatever instruction the program counter points to, and then it decodes that instruction, executes it, increments the PC to the next address, and this cycle repeats until your power goes out. This is normally where I cue some joke about Icon's power going out, but I'm going to guess and say that the Icon towers are pretty empty right now, so it doesn't work. Now, what this looks like in terms of the diagram is we have our address space. Now, I know in CS136, you typically had more segments in the address space. We're going to simplify that for this course. We're going to have just 3 segments in our address space: the program code, the data, and the stack. And if you recall, we always put the stack at the very end because we want there to be lots of space for our heap to grow and lots of space for the stack to grow. Our program counter is a special register in the CPU, and it's going to point to an address in the code segment. And then the CPU registers will have various data in them, and the stack pointer register, of course, will have an address of something on the stack in it. So we grab something from the code, we decode, we execute, rinse, and repeat. Single thread execution. All right. Now, I'd like to also take this opportunity to review a little bit of MIPS with you. Now, you are not going to be writing any MIPS assembly code for any of our assignments, but if you're going through the source code of OS 161, you will see multiple references to registers and some functions that are actually assembling. So it is important to know, how does OS 161 interface with the MIPS architecture. As normal, MIPS is a 32-bit architecture, and it is a RISC architecture. That's a reduced instruction set, and it has 32 registers. Now, if you're sitting there wondering, why do we keep coming back to this MIPS architecture? Isn't it just some kind of toy that was made up so we could learn 251 and 241? And the answer is it's not. MIPS, by the way, is real. It is a real CPU. And on many of my co-op terms, I was actually doing development for MIPS architectures. It's quite fun, actually. There's some very, very interesting and curious MIPS architectures out there. And in fact, if you have ever owned a PlayStation 1, you had a MIPS R3000. And a MIPS R3000 is exactly what our operating system is running on. And if you had a PlayStation 2, well, guess what? It had as a coprocessor a MIPS chip as well. So MIPS chips were actually quite popular in the day. Not so popular anymore as ARM has kind of taken over. But I think you'll see as we start to look more at ARM that MIPS and ARM actually have a lot of similarities. But let's go back to reviewing our MIPS registers. So as you remember, there are 32-bit registers for MIPS, and register 0 is always being used to hold 0. The same is true here. Now, our operating system has some conventions that both the compiler and the operating system are obeying and agreeing to. And the conventions are as follows. Register 1 is reserved. And as our registers 26 and 27, which are known as K0 and K1, we're not going to use them for general purpose registers. Registers 2 and 3, which have been named inside the operating system as V0 and V1, are used for return values from functions. Now, it might seem kind of confusing to have two possible return values from functions, but when we discuss processes, this will make perfect sense to you. We're going to leave it for now. To handle arguments to functions, we have registers 4 through 7, which are referred to as A0 through A3. Does that mean you are restricted to having 4 function arguments? No. If you need to have more than 4 arguments, you simply put things on the stack or in the heap and pass the address through one of these 4 registers. Then we have the S's and the T's. These are our general purpose, general use registers. The T's are the caller save, which means that before the function can use them, or before you call a function, you must save them. The S registers are the callee save registers, which means before the function that is called can use them, it has to save and restore those values itself. Now, why do we have this particular convention? How is it decided upon? Well, the compiler has to decide which registers need to be saved before they get used between function calls. Now, we could just save every register before we make a function call, and then all of the registers would be free use, but that doesn't seem terribly efficient. So what we're going to do instead is the compiler and the operating system have agreed to this particular scheme of T registers being caller save and S registers being callee save. This is going to come into play in a minute. Then, of course, we have register 31 as the return address, and we have our stack pointer and a global pointer as well. All right. Now, I'd like to review what happens on the stack when you call a bunch of functions. So we have function A. Let's move this video back here to where it was. Function A is going to call function B, and function B is going to call function C. So if we were to look at our stack, which has been drawn with 0 at the bottom and the high address at the top, what you're going to see is that we have function A is at the highest address, and there's its stack frame there. And there's function A stack frame there. And then function B gets called and its stack frame is in the middle, and then function B calls function C, and there's function C stack frame. When function C returns, its stack frame will pop off and we'll go back to function B, and then B's pops off and then we go back to A. Now, how does all of this work in a multi-threaded space? Because how are we going to handle each of those sequences of instructions having their own program counters, having their own stacks? Well, maybe we should ask ourselves, does each thread have its own, of the same program have its own program counter? Does it have its own register values? Does it have its own stack? And the answer is yes. Each thread is going to be executing possibly at a different rate. So we're going to keep track of the program counter for each thread separately. Does that mean that your CPU has a separate program counter for each thread? Of course not, because we don't know as hardware how many threads we're actually going to be running. So the running threads will have program counters that are actually stored on the CPU, but any thread that is not currently executing will store its program counter on its stack until it gets used at a later date. Now, we need to discuss the concept of stacks with a multi-threaded program. Do all of the threads share a stack? That's possible, but it would be an absolute memory management nightmare. So instead what we do is each thread has its own stack. What about address spaces? Do each thread have its own whole address space? No, it doesn't. All threads of the same program share an address space, which means that they have shared access to the code segment, shared access to the data segment, but since each thread has its own stack, any local variables are private to that specific thread. Now, this is interesting because it means that threads can share program code. It means that threads can have shared access to global variables, and threads have shared access to the heap. There are advantages and disadvantages to this particular piece of information. An advantage is that the threads are going to be able to communicate with each other. For example, if the threads need to talk to each other, they can use a global variable or a heap variable to actually pass information between each other. The downside, of course, is that what happens if two of those threads are going to read or write at the same time? We'll discuss the consequences of that and how to solve that particular problem in our next module, though. Now, the thread stacks, they are separate, which means any local variable is private to that thread. So, if you want something to be private, simply make it a local variable. Now, how do we handle having multiple stacks in the address space? What we're going to do is we'll allocate some space at the end of the address space for each thread's stack. Now, you've been taught in 136 that we always give lots of space around the stack to allow it to grow to a large size. Well, we have to put some restrictions on that. If we let each thread's stack just grow to an arbitrary amount of size, you would have individual thread stacks overriding each other. And as you can probably guess, that's a very bad thing. So we're not going to do that. And in fact, operating systems actually have a maximum stack size that a user program can have. In OS 161, it is a fixed size that cannot be changed of 48 kilobytes. That probably seems very small, but if you're only like sorting 100 numbers or counting from 0 to 120, you don't need a big stack. Now, what about the stack size on the computer sitting in front of you right now? You might be thinking that its stack size by default must be hundreds of megabytes, and yet it's not. The default stack size on most machines like Linux and Windows and Mac OS is only about 1 or 2 megabytes in size. However, there are many system calls that you can use to actually expand that stack size. Now, if you'd like to run a little experiment to see how big is the stack on your computer, try to create a really large array on the stack and see what happens. Is there a maximum size? Now, if you can't create a sufficiently sized maximum array using just integers, create a large structure and then create an array of those structures on the stack. How much memory can you actually store on your program stack? That's a fun little program for you to write at home if you're bored. All right, now, before we talk about how threads are implemented, I'd like to take this opportunity to do a sample problem. Now, I have posted all of the sample problems to Piazza. I'll show you here, actually. That's the best way to do things. So if we open up Chrome and let's just go to Piazza here. Okay, maybe that's not what I want. There we go. There's Piazza. So if you go on Piazza, you will see extra lecture content and guides. And if you go in there, you'll see sample problems and there's a zip file. These are sample problems that we would normally do as in-class problem breakout sessions. Unfortunately, since we don't have the ability to do that, we're just going to introduce the problems here in these lectures, and then what's going to happen is we will take them up in the following episode to give you a chance to give them a try. Before I actually move off Piazza, another thing I'd like to point out is there's also a bunch of posted guides and assignment guides, and please take an opportunity to answer this question here, which says, if you could ask the creators of something like Unix just one question, what would you ask? All right. So let's then go over to our sample problem of the day. This one, if you are following along, is called fork print. There we go. So again, we're not going to be able to see this all on the screen and readable at once, so I really encourage you to actually go home and open up fork print yourself. But let's discuss just what this problem is before we move on to another demonstration. So we have our main function, which calls this helper. And the helper function inside, you will see if I is less than 3, it is going to print the value of I, and then it's going to fork 2 threads, and the thread it's going to fork is actually itself. And each time it forks itself, it increments I by 1, as you can see here. All right. If I is greater than 3 or equal to 3, we don't fork any threads. And if I is equal to 0, we're also going to do a print here. And then when we forked all our threads, we call terminate or thread exit to stop the thread, although this wasn't explicitly necessary. So the question then asks, based on the little bit of code that we have given you, which of the following outputs are actually possible given this program here? Now, a couple hints I will give you about this particular problem. First, you have to ask yourself, how do multiple threads run? Remember that they don't necessarily start, run, terminate before the next thread gets to run. It's not to say that's not possible. It's just to say that that doesn't always happen. You have no control whatsoever on how threads are actually going to run or what order they will run in. Keep that in mind when you're doing this particular problem. The other question that you should ask yourself is, where do I print and where do I fork? I think with those 2 hints, you will be able to answer this particular problem here. So again, this is fork print in the sample problem file that is posted on Piazza. The other thing I want to mention about the set of sample problems you'll see here is that these are all previous midterm problems. Now, I know you're not going to have a midterm. You're going to have quizzes instead. But these problems are a really good way of testing, do you understand the concepts we're talking about? All right. So let's go back to our slides here. Not our slides. What I'd like to do now is I'd like to take this moment to look at how do you debug OS 161. The reason why I want to do this is because through the debugger, I can actually show you the contents of thread stacks. So it's very relevant to our conversation at hand. So first off, in order to debug OS 161, you are going to need 2 terminal windows, and it's absolutely critical that those 2 terminal windows are running on the same machine. So if you're SSHing into the school servers, instead of just using linux.student.cs, please find the name of a machine, and you can find them on CSCF's webpage, and log into a specific machine twice. All right, so I'm not logged into the school machines. I'm just on my home machine. Yes, I have OS 161 running on Catalina. And what you're going to do is you'll see I have both of my terminals open in the root directory. So I'm going to clear both of these up. So in my first terminal, I'm going to start OS 161 with a very special flag to tell it, please wait for a debugger to connect. So we type sys161-w to wait for the debugger connection. And then you type the kernel you would like to wait for. Open. Now, when I push enter, the message that you should see is waiting for a debugger connection. This is your cue to go to your second terminal. And here we are in the second terminal. Now we can make this a bit more interesting. Let's separate it out. Here we go. And let's do this so we can see both windows at the same time. There, that's a little bit more interesting. So we've got one is waiting for debugger connection, and now we're actually going to start the debugger in the second window. So it's important that you don't run just plain GDB. You need to run our variant of GDB, which is GDB, but we've modified it a little bit to support our MIPS simulation. So run CS350 GDB. And it's very, very important you specify which kernel you're going to run it on and make sure that it matches the one that you are trying to run. So I am running kernel assignment 0. I push enter. Now, nothing has happened. Nothing has changed. GDB is open, but our operating system is still, or our simulator is still actually waiting for the debugger to connect. So what we need to do now is we have to tell GDB where to find the code for OS 161, but we also have to tell it how to connect. So in our GDB window, we're going to type, and by the way, all of these commands are available on the course website. We'll type this command here. Make sure it matches with the version of the kernel you're trying to debug. So we're going to debug assignment 0. So you'll see now source directory searched. So that's good. And now, but we haven't actually connected. So now we need to actually perform the connection between GDB and OS 161. So this is where we use target remote Unix sockets GDB. I spelled it wrong. Make sure you spell it right. There we go. Now, you will notice that the state of GDB has changed, but the state of our OS 161 has not. And that's because we haven't actually told OS 161 to continue running. GDB is connected, but OS 161 hasn't been told, hey, you can start running now. Before I tell OS 161 to start running, however, what I'd like to do is place a breakpoint. Now, a breakpoint is a little trick we can use to pause the execution of the program when the program reaches that particular line of code. Now, I am actually going to put a breakpoint in thread test 1 on line 64. To create a breakpoint in GDB, we use B. Now, there's a variety of ways that you can actually place a breakpoint. My favorite way of doing it is to actually specify which file and which line number I want it to locate at. So to specify a file and line number, I would say threadtest.c:64. So line 64 of threadtest.c is where I'm placing my breakpoint. GDB will confirm your breakpoint and tell you at what address it is and in what file and on what line. Pretty cool, right? Okay, now we're actually ready to run OS 161 now that I've got the breakpoint I want. So in the GDB window, type C to continue and unpause the execution of OS 161. Uh-oh. Oh, there it is. I forgot to scroll down. I forgot that it's put out a whole bunch of spaces. There we go. OS 161 is now running. Now, the breakpoint, you'll notice, hasn't been reached, and that's because it's in a program that we haven't actually run yet. So what I'm going to do then is I'm now going to run thread test 1. And when I run thread test 1, you'll see that the OS 161 window is a starting thread test, and then it pauses. And it paused because if you look at the GDB window, we reached our breakpoint on line 64. Now, if you're sitting there and you're wondering, I don't remember what this line is, what code was this, what function was this, how can I know where in my source code this particular breakpoint was? There's a magical command you can use in GDB to show you the region around where the breakpoint is. Simply type list. And there you go. GDB shows you a few lines that preceded the breakpoint and a few lines that follow the breakpoint. That should be enough to jog your memory about what exists. Now, what are the exciting things that you can do now that you have paused the execution of the program? Well, one of the things that you can do that's very valuable is you can take a look at the stack. To look at the contents of the stack, you're going to type BT for backtrace. Now, our stacks don't actually contain much because this thread doesn't do anything interesting. But what you'll see is at the top of the stack, or the bottom of the stack, depending on how you want to look at it, we have the mystery thing here. That's because this thread is very new and there's nothing beyond here. Thread startup is the function that was called to create the thread, and then the stack frame at the top of the stack is a loud thread, which is the stack frame for the function we're executing right now. Now, why is looking at the contents of the stack particularly useful for a multi-threaded program, or any program? Let's suppose you've written some complicated program, and for some reason you're getting an unexpected value. And the only way this unexpected value could arise is if a function gets called that shouldn't be called. How do you discover why that function is being called? Well, if you look at the stack's contents, you will see which function called it. And so now you can see, oh, I see now why this program doesn't operate correctly. So now we have a better sense of why our program isn't working. You will find the backtrace command to be very, very useful for debugging in this course. Now, backtrace is very useful, but there's another useful thing that we can do with our GDB here, and that is we can actually inspect the values of the variables at this point in time. For example, perhaps we're getting an output which has an unexpected value. Maybe we should inspect the values of the variables that were used to compute that value. In this case, let's just print out the value of number. So there's two ways you can do it. You can do print num, or you can do display num. Now, one of the really interesting things about GDB is that it understands pointer arithmetic. So I can do print the value of number, and you'll notice here it says cannot access address 0. The reason for that is because I just treated number as a pointer, which it's not. So I just tried to dereference null. Don't do that. But I can say print the address of num. And look at that. There's the address of num. Pretty cool, right? Now, if you have a structure such as the thread structure, I'll show you what the thread structure contains here. So the thread that's running right now in OS 161 is stored in cur thread, which is a pointer. And that's actually how threads in an operating system are described. Threads are actually structures inside of the OS. And information like the address of the stack and the program counter and so on is stored within that structure. That will make a lot more sense in the coming days. So cur thread is going to be a pointer to the current running thread's structure. I can print cur thread and you'll see that it shows me the address because of course cur thread is a pointer. But now let's suppose I want to inspect the contents of this structure. Well, GDB understands pointer arithmetic, so all I have to do is use the value of operator. And there we go. You can see that it actually prints out the complete contents of the cur thread structure. So I can see the name, I can see the state of the thread, I can see the address of its stack, and all of the other important information that are inside of the thread structure. So this, in a very quick moment, is how you will run GDB to debug OS 161. And I can't reiterate enough. It's very important that you use GDB to debug your assignments, especially for assignments 1 and assignments 2A and 2B. It's not to say that printfs won't be helpful. It's just that printfs can wreak a lot of havoc in debugging, as we'll explain. All right, now we're done our debugging here. So to terminate, we can just type quit, exit anyways, and you'll notice not only does GDB quit, but so does OS 161 in our simulator. Now, one thing I want to mention before we go on to discussing a few other topics is that those two little Unix little setup commands I used for GDB with dir and target, you can actually just write them into a GDB init, and then each time you run GDB, you don't have to type them manually. I should probably do that, but then I couldn't do this lovely demo, of course. All right. Now, one more thing I want to show you about threads before we move on to how to threads execute. Let's go back into the current directory of OS 161. And let's leave thread test in the thread test directory. So here we are back in kern. Let's go into the include directory. Here is where you will find all of the different include files for OS 161's kernel. The include file I would like to point out to you is thread.h. Now, if we scroll down in this file, you can actually see the structure of OS 161 threads. So we have a thread, and you'll see also that this code is reasonably well documented. The thread has a name. We have a state. We have information about which CPU it runs on. We have information about which program it belongs to. And then we also have a pointer down here to its actual stack. Where is that pointer? It's in here somewhere. All right, so there's our thread. There it is. There's the thread stack. Void star t stack. That is the stack for this thread. It's complicated. We'll explain a bit more why it's called a kernel stack in the fourth module. All right. So every time you call thread fork, OS 161 is actually going to create a brand new thread structure for you, and it's going to add it to the list of threads that the program actually has running. All right. So then, how do threads actually run? So concurrency is the ability to have multiple threads running or appearing to run at the same time. How do you actually implement this in an operating system? Well, there's a bunch of different ways that you could do it. The first option is hardware support. If you have some number of processors and some number of cores, and each one of those cores supports some degree of multi-threading, then you can run P times C times M total threads truly in parallel. So if I was to compute how many threads I can run in parallel on my MacBook here, I have an i9, so I have one CPU, I have 6 cores, and the degree of multi-threading per core is 2. So the total number of threads that I can truly run in parallel on this Mac is 12. The computer behind me, being a thread ripper, can run, I think it's 64 threads truly in parallel at the same time. That's pretty impressive. However, if we actually look at top here, top is telling me that the total number of threads that I have running on my computer right now is in the 1700s. I don't have that much processing power. So what else can we do? The other option is known as time sharing. Now this I've already kind of alluded to, but if you have more threads than CPUs, what you need to do to give the illusion of those threads running at the same time, and to also have those threads all making progress, is you need to rapidly switch between them. That is, you'll give each thread a short period of time, say 50 milliseconds to run, and when their time is up, they have to give up the CPU and let another thread take a turn. So time sharing is one way that we can overcome having only one CPU and one thread running at a time, but still giving our user the illusion of multiple programs running at the same time. Now, what is the computer in front of you doing? It's doing both of these things. Obviously, we can support some number of true parallel execution. And in my case, it's 12 threads can execute. But I have way more threads out there than that, which means I'm using both hardware support and time sharing to create a certain degree of concurrency. All right, now I'm going to leave this here for today. On our next episode, we're going to dive into how time sharing works. We're not going to discuss how hardware support works because we feel like it's kind of obvious. If you have a bucket with 4 holes in it, then you just put one thing in each hole. Time sharing, on the other hand, is much more complicated and has to actually be implemented as part of the kernel. So in our next episode, we're going to discuss how to implement time sharing. We'll also take up the problem that we discussed a few moments ago. All right. Have a good day, everyone, and we will see you on Tuesday of next week.
Panel. That was a tough one. We thought we'd do much better. Now, in just a moment, we're going to meet tonight's mystery guest. But first, for a message from Remington Rand, we switch you to the CBS remote unit.
This is weather, one of nature's ever-changing mysteries. It affects every one of us every day of our lives, and yet we know relatively little about it. Weather, that's something we'd all like to do something about, isn't it? And so tonight we've brought you down here to Remington Rand's New York Computing Center in order that we might show you that something actually is being done about it. The hero of our story tonight is the giant electronic brain developed by Remington Rand, UNIVAC. Now, recent experiments show that future use of UNIVAC may give us faster and more accurate weather predictions than were ever possible before. You see, UNIVAC can take the past histories of thousands and thousands of storms, analyze them, compare them with developing conditions, and make predictions, all in a matter of minutes. Calculations that would ordinarily take hundreds of man-hours to complete. Data from guided weather rockets, radar observation stations, weather stations, all of this can be fed into the computer through these magnetic tapes at a rate of 12,000 numbers or letters per second. The memory tanks make immediately available 12,000 additional units of information. And all of this complex weather data is analyzed in the heart of the UNIVAC, the electronic central computer, capable of making over 2,000 mathematical calculations per second. Now, here is where we get the answers. You might call it the voice of UNIVAC. Actually, it's a high-speed printer that prints results at the rate of 600 lines a minute. So you can see that UNIVAC is both fast and versatile. But most important is the assurance that UNIVAC will give you the right answer. And that's made possible by UNIVAC's unique ability to check itself on possible errors. Let's watch right now as UNIVAC puts itself through one of these self-examinations. Here it is checking on some of its own units. It's really an amazing system, isn't it? Amazing and yet so wonderfully practical. Remington Rand makes 4 basic UNIVAC models. The general purpose UNIVAC, which you've seen tonight, UNIVAC Scientific, UNIVAC File Computer, UNIVAC Punched Card Computer. Each of them capable of literally hundreds of applications from weather forecasting to complete business control. Today, UNIVAC is saving time and increasing efficiency for business, industry, and government. And of course, that is the business of Remington Rand.